Hi, everyone. Welcome to another Haskell study group. I'm your host, Ram Vedam with Atlanta Functional Programming. Um, we're going to be discussing today two final topics in our journey in monads. One is related to um, the issue of different uses of our Haskell um, uh, different different uses of different monads that are available in Haskell for you. There are a lot of pre-built ones that you could simply look at by typing in control I, sorry, colon I monad or info monad, and you'll get the same thing. And all these instances that are available are instances available at your disposal. These monads are fairly there's a fairly small subset of them, as you can see here. Some of them are related to some of the libraries that we've been using up until now to verify our monads, particularly the quick check library along with checkers, which gives us some monadic laws already or monadic properties that are at our disposal if we wanted to go and validate our monad instances. In addition, we have the list monad and maybe monad, both of which we're going to be covering today, and then of course the IO monad, which we will cover at a later point when we start talking about IO. Now, obviously, for folks who have been following our tutorial series and have been following the book, the IO monad has already been kind of introduced in earlier discussions when we talk about read line. But mind you, read line and put string line are while part of in return the IO monad, we didn't actually discuss the implementation of the IO data type itself and how one might end up using that in various situations, not least of which is using the IO monad with the IO data type when we're constructing and creating functions that might end up returning IO. Now, the other topic that we'll be discussing is actually related to function composition when dealing with monads. And in particularly, we're going to be talking about the Kleisli operator and the Kleisli composition, which takes in two monads and or two functions that return monads and actually returns the composition of those two functions with monads. In order for us to do that, of course, there's going to be some work involved. Primarily, we're going to revisit how composition actually works and then work through an example of defining something that would ultimately result in us becoming or discovering the Kleisli composition operator or how one might actually go and implement it. Um, Again, as usual, those who have been following our discussions and following the journey up until now, if you do have any questions, by all means, go ahead and throw it into the chat window and we will address them as they come along. If you watch later, please comment on the YouTube video, both either with questions that you may have of material that I have covered thus far, um, or comments or feedback related to how the material that I am presenting today is presented. So this way we can go back and address any sort of weaknesses in later videos and then come back and talk through some of the more confusing concepts that people brought up in the YouTube comments. The point of all this stuff is not just for you to read and have complementary or supplementary material as you read through the Haskell book or any Haskell book for that matter, but we are trying to make sure that the AFP content that related to all this material up until now stays at a level at which all of you can use as a resource and make this ultimately your resource on how to understand some of these concepts if and when you decide to dive into the Haskell journey, or if you have already, if you decide that there's a particular concept that doesn't necessarily match your current thinking. Um, Okay. Sorry, there looked like there was a little bit of a stall when I was looking at the YouTube stream just to make sure things are going on. So last time we actually went quite far and we created an example here of a data item that we defined, including an implementation of how we might end up defining a monad for this data item class that takes in an integer. Now, remember, since a monad is essentially a concatenative map, in order for you to, sorry, a concatenative, in order for you to implement uh, sorry, the monad for a data item, you'd have to implement essentially what would be equivalent to a concatenative map. Um, but preserving structure, you would have to actually make the monad into what's called an applicative functor, which is why we end up having to define the applicative instance for the data item as well as the functor instance. The functor instance, of course, we've kind of talked through that already. Would require us to implement fmap as the bare implementation of it, and then for the applicative instance, because we need to deal with the monoidal associativity, we need to implement both pure, which essentially, as you could see here in our monad instance, is the actual same implementation for return in the data item monad. And of course, the apply operator, which is then leveraged on when we go in and construct uh, so- something equivalent to what we see here in lines 38 and 39 mainly. We end up having this simple apply function that behaves roughly the same for each uh, application of the apply function, the applicative apply function operator. All right. Um, you may recall one of the reasons why we did not actually call out um, the n prime section here. It's because this here is ends up uh, requiring us to have two different uh, functions for the data items. So uh, of course, here you could see data item n prime b is equal to f of a, is obviously going to allow us to create n prime plus n plus n prime comma b for some data item b. This data item b is what's ultimately going to be returned for the different type when you apply to your data item to your monad. And that actually will hold, if memory serves correctly, this f of a essentially has its value because the return of this function here um, is alias to this data item that's being created on this side, on the left-hand side. All right. And we've kind of gone through some of this stuff related to setting up our things for quick batch, and we noticed that if you implement your monad restrictively like this, you'll end up having to um, you wouldn't get the appropriate errors that you would in this case because when we go ahead and run this here, we'll end up seeing that our because we've already defined how the monad it correctly defined the monad instance last time, these tests will all pass. And remember, as you could read this through, the quick check is already going to give you implementations not just for the identities and laws for monads. Okay, and remember the laws for monad is left identity, right identity, associativity, all right, and then pure. It's going to also actually effectively call the applicative instance apply, which is essentially equivalent to calling the star operator that we've defined earlier in our applicative instance for data item. Okay. And this is the same thing for applicative. Applicative is going to go through and test its applications using checkers. But then, in order to make sure that we are mathematically complete, it will go and test the functor properties because, as you know, um, applicatives are monoidal functors. So you get the monoid behaviors in the applicative instance and how you define them, and then the functor ones is expected to be implemented already, which is mainly identity and compose. All right. So let's talk about some very simple monads that are already available in uh, Haskell. One of them we kind of been using, even though we didn't explicitly say that there's a monad and that it's a list monad. Okay. If you look at how it might occur, the main thing to look at is the function signatures, and specifically the function signatures of the bind operator, which we all know requires you to take a monoid m as a requirement. Okay, and in this case, um, and it will take in a monoid of a, and then a function that takes an a monoid of b, and then returns a monoid of B. Sorry, it'll take a monad of A and then a function that'll take an A and return a monad of B and then returns a monad of B. Now, in the case of the list operator, what this is going to be converted to is literally nothing more than, since list has defined, as we saw earlier, a list instance. This is just simply going to be a list of a function that takes an A and returns a list of B, and then returns now a list of B. Now, folks may notice that when you see this in the book, they write it like this. For whatever reason, the main reason that they write it like this is they're treating this as a different type than, say, this, which actually is a type constructor for the empty list. Okay. Um, I never actually checked to see if we need to write that in general this way. I don't remember if there's any particular issues about it, but you know, obviously you can also take the shorthand of this and just say A, B, and then oops, sorry. So all three are perfectly valid. Um, This is the generic one that's going to get parameterized. This is what's generated when it finds that there's a list instance. This is just a shorthand of the previous section. All right. Pure is the same thing. Pure again. Remember, return is equal to pure in almost all situations. It should actually, otherwise you'll invalidate the applicative laws. Um, so you'll almost always end up having return has pure, and return, as you know, takes in something that's expected to have a monad defined for it, takes an A and returns a monad A. Okay, so in our case here, if we have return and it takes in A, it's going to return a list of A. Okay. This is important because, again, when we define functions, remember, there needs to be, or even applications of functions, remember that there needs to be a way of lifting the function into, or lifting the value into, depending upon whether you use left identity or right identity associated with the apply operator. Um, it needs to be a way of lifting that thing into the monadic space before it actually does the application. And it's using the notion of the applicative in order for it to actually go and lift this guy up and then move it across the monadic transformation pipeline. Now, we can define a couple things here to make things pretty quickly. A simple example of this is let's just um, use um, Let's just write a simple filter and then do an even. Okay, so you know, we could simply do this. This is an example that I think is important that best illustrates this. This is um, let me see, what would be the best thing to test this out? Um, I don't really want to add a filter. Okay. Um, let's say, for example, we want to go ahead and do double. Yeah, we'll just do this. Uh, let's do twice when even. This is an example from 18.6 that I think best illustrates this. It takes in a list of integers that you're attempting, and it's going to return a list of integers. Okay. Now, twice when even, when defined, will take an axis as an input, and then it uses do syntax for this, okay? Because obviously do's is doing, remember, the sequencing operation that we looked to last time. You could certainly implement this using the sequencing operation. It's not necessary though if you use do. Here, what we'll do is we'll unwrap each value in the input list into an X, and then we're going to check to see if X is even, okay? Um, and if you want to know what even is, even basically takes in an integral and then returns a bool. And what we'll do is if even, then what we're going to do is we're going to go ahead and multiply, um, not multiply, add X to X. Otherwise, we're going to go ahead and just do this. Okay. Um, one second. Let's go ahead and load this here. We're going to reload monad overview. We'll see that our definition is defined. Okay. So now what we'll do is we're going to call twice when even on just simply 1 to 3. Okay. And notice what happens is when we call twice when even 1 to 3, it's going to generate 2, 4, 4s, and 6. And this should make sense to you because what it's doing is it creates it's calling fmap essentially into this list, and what it's generating is 2, 4, 4, because 2 is obviously even, and then 3 is not even, so it's just going to return 6. Right now, once this is done, obviously, this clearly is not what we want, because although this is creating the right output, this is creating a list of lists, right? So what we want to do is we want to go and reduce that. So as we mentioned, the way you implement reduce is using the join operator. So it will call join essentially on this list, and join will flatten the intermediate results, that each of which returned a list of one or more elements into the list that we ultimately got, which is 2, 4, 4, 6. Okay. Um, this is pretty straightforward. Um, you can also use this to say have a filter, like so. And what this will do is if we call now um, our twice one even um, function. Um, get this? Oh, I can't get this. Okay, one second. Do this. Here we go. So see now what we'll end up getting is only the intermediate results of the 4-4. Now, again, if you work out the evaluation of this, your intermediate results is going to be a list of values. Okay, you can see this every time. The code, though, is written in a very sequential manner, all right? And that's the beauty of using do syntax. And yeah, it hides the fact that what you're ultimately doing, as you saw in, I think we have an example of this before. Um, we can, do, if you recall, you can actually do this equivalently. Compare this to, say, um, this twice when even seek. And look at this and recall twice when even seek given x's. We could do x's bind into the function that takes an x and returns um, uh, following. Um, let's say if even x, then we need to obviously do this and um, plus x, x plus x, else return here. This should work. Let's see. Okay, let's try our function here. You'll see it's the same thing. Now, this is another way of writing it, okay? Um, and it is a quick shorthand, but if you see here, you're really hiding do really makes it clear that what you're doing is you're first grabbing each value x and then checking to see if it's doing. This here is essentially showing you a pipeline, right? It's constructing and making sure that the input is sent from left to right, one at a time. It'll make sure that each value is sent through this pipeline. Different advantages come from using one versus the other. In the second case there that you see, um, it might be useful, say, if you're adding functionality as you're building up this sequence or set of operations that you're composing that you might want to end up doing something like this. Um, but I would make it clear that right now, because you aren't using named functions here, we're using uh, we're using a function that takes in um, uh, it's an anonymous function and it actually writes some logic into it to make it slightly it's okay. So to put it in a way that's pretty simple, the bind operator has it as assigned because you're using an anonymous function might get unwieldy depending upon the size and complexity of the algorithm that you are implementing. In this case here with the even sequencing set here, it's pretty straightforward. You can actually look at it. You don't have to worry about it. It actually just kind of makes sense. But there are cases where it becomes fairly obvious, complicated, where you may want to, leverage something else, right? So I'm not going to go into more detail on this. I'm just kind of showing you and compare this as a review to remind you that essentially the do syntax essentially converts into that second thing that we see right there. The second monad that we're going to cover is the maybe monad. All right, the maybe monad is a little bit more interesting. Than say our list monad just because we use the list monad quite a bit. So um, the maybe monad ends up probably uh, being a little bit more useful in terms of how one might um, how one might end up leveraging monads to actually go and cover and safely transform different operations together, because the maybe monad can return just or nothing, right? So an example that we could implement here is the uh, you know like, because we were dealing with what would be an interesting thing. Okay, we'll just do the standard person example that I always end up doing. So let's say that we have person, which person taken, and I'm going to use the record syntax for this just because it's a little bit more cleaner in my opinion than using straight up um, the normal type syntax that we're all uh, familiar with, like with data item. So in here, we're going to say that a person has a name, right? We're not doing first name, last name. It's unnecessary. Um, for this example, we got age, which itself is going to be an integer. And then we have occupation, which it's a string, all right? And let's go ahead and we're deriving equality and show so we can get some nice things about this, okay? And then, I'm just going to go ahead and write some convenience uh, uh, functions here just to make things a little bit easier. Like, for example, if we do, you know, get name, okay, takes in a string and give it maybe string, and get name on the empty string is going to be nothing, but get name on an actual string is going to be the actual string. We're going to do the same thing for in a similar fashion for occupation and actually let's keep this simple here. For occupation, it's going to be get occupation, okay, because it's going to be the same thing because they're both of string data type. What is this complaining about? Dear. Yeah, hold on one second. Oops. Oh, deriving. Oh, sorry. I forgot that I could write it this way. This has nothing to do with these commas. It's the fact that I'm trying to create multiple things. Now, all right. Um, and let's go ahead and quickly get age here. It's taking an integer and maybe int. And we're going to do is we're going to define this just a little bit different. We're going to use an if else here just because it makes things slightly easier. Um, get age x if x greater than 0, then just x else. Go ahead and do this. Nothing. Okay. So we now have our stuff. Let's go ahead and do that. And what we're going to do is we're going to make a constructor, okay, called make person. All right. What this is going to do is it's going to take an um, so each of these here should really be validators. All right. So what this is going to be is let's call these actually valid names. Valid, valid, valid. Oops. Yeah, actually valid. Go ahead and do that. Keep things interesting. Okay. And we're going to go ahead and say make person. We're going to have a name. We're going to have an age. We're going to have a occupation. Okay. Now, to make sure that all these checks are added, you could use, say, guards to actually go in and validate each piece of the names, and instead of writing a bunch of if else's. So you could do, say, for the first one, if we have a valid name, if we got nothing, then we're gonna not obviously return nothing here. If we have something, all right, like let's call it just name, then what we'll do is go into the next case here, which will then validate our age in our case because we're going to check the age. Secondly, again, if we have nothing, you want to return nothing. Otherwise, you want to go ahead and check to see if you have some sort of weight and, sorry, some sort of occupation. And then if you do uh, age, then if we do case valid occupation, and a valid occupation is nothing more than going to be a non-zero name. All right, we're not going to check to see that it's a valid profession. Obviously, if you wanted to, you can actually go and check if it's a valid profession or not, and then you have these two cases here. And if you have all of them, then obviously then we have a valid person, so we can go ahead and construct. Let me do this. Name, age, occupation, and and what's the name of this? Um, maybe A. What's the actual type A? So there might be something here. Oh, got it. I have to go and write, I think, here. Um, just go, and we need to use this. And just make sure. This is bound here. This binding shadows an existing binding. Okay. I'm just gonna say name age. Having a bunch of typos just because I really don't want to add like. Why am I doing that? Actually, do what since we're in Haskell. That all right. Now we do not have our. All right. Now this is going to be good. Load it. We're good. So when we call this, this is going to go ahead and obviously if we end up using uh, if we go end up using say um, um, this guy and call it on any of these, all right, say 35 and software engineer, you're going to end up getting what we're expecting, which is nothing. If we just simply call this guy so you'll see that you'll end up getting a valid yes. All right. But clearly, writing these kinds of validators and these kinds of checks in this kind of code can get fairly complicated and fairly difficult very quickly, right? So one additional thing that you could do is make and different. Let's say we use the same signature here. Make person prime, but this time what we're going to do is we're going to use name prime, age prime, weight prime, new syntax. And name double prime is just valid name prime. Age double prime is going to be valid name, valid age prime. And then occupation double prime is just going to be straight up from the occupation. And if all this works, then we could just return um, just then provide a person um, name prime, age prime, occupation. And this is going to essentially do the same thing. Okay. Notice that this is, did I spell it wrong? Oops. Wait, there we go. I'm thinking of the example that's in the book, and I'm writing an equivalent here. That's essentially the same idea. Because the book already went through too much details. I don't think I need to show you guys what the book already has done. I wouldn't even do the explanation justice. This is kind of the same idea of this one, which is basically we have a set of validations, we have a set of code, we have a set of three argument strings here, and then we'll end up getting a constructor. Now, does this actually match our what we have earlier? Well, let's try this out. Um, Load, everything is good. Let's go ahead and grab our, see what happens. We got nothing good so far. Let's see here. Let's create John Doe. We got a valid thing. Okay, so we have takeoff. So if we do this in any of these, we'll get zero. Nothing has an answer, and if we get a nothing has an answer, we'll automatically spit out, and then the rest of the objects is just going to be incorrect. So we'll end up having a very nice little validated test program. And this here, I think everybody would agree, is easier to extend and it's more maintainable than something like this. So it is possible to write guards, but you need to know when and where it is appropriate to use them. All right. Um, So this is pretty neat. Pattern matching again comes to your to our rescue when it comes to defining the validators. I don't think I can't speak any more highly enough of writing patterns like this versus having to do if else statements for different patterns in existing programming languages. In ML, variants like OCaml and stuff, you'll have the case of type pattern matching too. But they do not have this left hand side sort of let's write rules for different cases, at least not as far as I know. So if you're looking at this from other languages, um, keep that in mind. This is one of the nice features of this. Now, combine that with the ability to write a monadic instance like what we saw here, and you have a pretty powerful combination to be able to write sequences of stuff behind the scenes, add structure and delete structure on the fly. So that's the maybe monad. Are there questions so far? None of this should be surprising. Um, By the way, we could also define this using the bind operator. Uh, I'm not going to go through that. If you guys want to see an example like that, the book covers that example. But just like we did earlier with this twice check, you could certainly define something like it like this. Um, but it becomes fairly complex with multiple function applications of anonymous functions taking in all the different values. So it becomes unnecessary to go and unwieldy to go through that example. In fact, I think I could also use a different guard than the one that I just wrote. I can actually use um, in here, instead of doing this, I can also use this. That's wicked. Um, okay, okay, and then this should work. Oh, otherwise, there we go. Time. Oh, called make person, not make person prime. Give me a second. I did not do this earlier. Let's see what happens here. This. Oh, um, yeah, still the same. So it doesn't matter if we use make person or make person. Um, Final one that we're going to be covering is going to be the either monad. Um, the either monad is the one, if you remember, there's either it has a left side or a right side. Left and right are the names of the 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 data constructors for the different types, has indicated by if we do a info on either, see here, either is either left A or right B, and it's a higher kind of type. Um, this monad actually has some interesting rules, and it's particularly useful if you are uh, um, when you're dealing with like error handling. Um, the bind operator specifically would use either it has an error or it has the actual value. And you could see examples of the signatures of this if you just simply look up the either implementation that you on I think you can actually look it up on Google, and you can see a simple example implementation of that the either type itself. Now, the either monad also will take into account some of this information. The one thing that's peculiar about the either monad is because it's either left or right, you end up defining just like pure for the either applicative um, for either. Um, return basically, which is essentially lifting from pure, it will require you to take in essentially, and the signature is going to be an A, and then it will return an either A, E, or A, right? Mainly so that you have the left hand side uh, uh, available as part of the type, even though you might be only dealing with the the right, which has the successful value. All right. So let's do, let's see here. We'll do the, so this is, so another example of this either type is going to be following kind of the same lines that we ended up dealing with here. So we can actually end up using the either monad instead of the maybe on just checking to see if we are dealing with a um, a senior citizen or not. Okay, we can actually do it this way. Okay. Um, again, this is how you would end up leveraging quite a few of these different kinds of types. You're going to end up creating like say validators, and then probably leverage this as you filter out information. Okay. So we have validate year already. We have valid age and so forth. Um, so what we're going to do is we're going to end up using, um, let's go into, yeah, create a, oh, a function called, say, eligible for retirement. All right. That takes in, say, um, and what we're going to do is in order for us, it's going to take in a person, and then it's going to give us either um, a let's use for the left-hand side um, different reasons for ineligibility. And obviously, you can expand this for in retirement ineligibility. Eligibility. And we're going to use just either, for example, um, too young, then you pass in the person, or uh, they might be, for example, um, a different nationality if we add nationality to our person. Okay. Uh, oh, not citizen person is probably what we should say, because you have to be a citizen, be in order to be associated with say SSA benefit, Social Security benefits, and so forth. Um, uh, and the name of this, it can go, it can be named anything. Right now, I just uh, an eligibility error, or we could call this eligibility error. And there's different reasons why you'll get this. And let's see. Oops, we'll do that. Oh, we don't need that. And let's see. What other reasons? You might have one or two reasons here. I think we're good here for now. And this is going to take this, and it's going to be either retirement eligibility error or person. Okay. And what we'll do is we're going to create a couple of functions here. Um, one is going to be uh, eligible. Instead of calling valid age, say it's going to be called eligible age, just so that we don't deal with the problems related to our our um, shadowing when we're dealing with the shadowing of symbols, because we've defined a valid age earlier on. This is going to take in. Let me just do this way, and that's it. Um, retirement eligibility error or person. Um, an eligible age takes in a P, and if um, uh, right, we need to actually grab the person age. We're ignoring the other two. What we'll do is um, age greater than zero, sorry, less than say 65, then we end up doing a left, um, too young, and then we're going to provide the person. Okay. Sorry. Actually, We do this. We don't really need this. We could just say left, too young, dollar. Then we can do, we do not, I don't think we necessarily need this. Just that. Um, it might complain, but we will see. Um, otherwise, we have right, and we end up using, say, um, oh, we need to pass it. We do need the actual person object too, don't we? Um, let me see. How do we move the persons available at the same time? We would have to be able to deconstruct the object. Got it. We're gonna have to use name, age, and create the person each time. Okay. Now we do right. We create a person, name, age, occupation. Because we're looking at equality here, not necessarily we're looking at um, the object EQ coming from a Lisp standpoint. All right. So we have this. Um, this looks good. And then in that case, we can actually do this too as well. Person. And then we can actually do this. Um, and we'll just go ahead and add the name occupation. Then we have, we might end up adding a couple of others, although this, for now, I think we can just work with this right now. Um, and and we're gonna go ahead and make this into the uh, let's we don't need that for now. Let's see what happens if we do this. So eligible for retirement is actually just going to go ahead and give you a reason. Otherwise, it's going to give you the person back. All right. And um, here again, we're going to use a deconstruction. Um, and obviously, this is going to be inefficient because I'm creating multiple copies of the object multiple times. So this isn't going to actually be efficient. But I wanted to kind of illustrate how one might go and use these full objects across. And later on, when we're constructing more advanced programs, I will show you ways of there might be ways of actually addressing how to pass in an object in another way. Remember, the one thing about these things though is you can't just there aren't you'd have to provide accessors for some of these things, and I'm not entirely sure how like p dot age or how to actually get the accessors right now on the top of my head. Um, don't remember exactly. I think we've covered it at one point, but it's right now evading my memory, and I don't want to start discussing how to clean up some of this stuff. At some point in time, we'll clean this up just before we move on. But for the time being, keep in mind that this is definitely an inefficient version of what we could do. So we're going to go in and check to see if we have a valid age, and let's just say um, eligible. And age eligible is probably what we want to say. Age eligible, and um, here, obviously, uh, we'll start with just grabbing um, eligible age and okay, so we have this. We're gonna go ahead and grab this guy and hold on. So V yank paste. Okay, and now that we have it, um, what we're going to do is uh, we are going to leverage um, actually we could just simply return this right now because we're not actually adding any additional checks. So here, I think I could just simply do this, see what happens. This ours. Oh, oops, do. Um, must be an expression. So once we grab the expression, we need to be able to actually check to see if we're dealing with it. Okay. So if this is the case, what we'll do is, um, does do expression. We have an object here. Um, Let me call this eligible person. And let me see if I can do um, person, eligible person. Let me go look this up. This was to access. Uh, it was. Um, it was. If we do. Let's see here. There is. I might want to use a different thing here. List tuple. Let me see. It was. Once I have that, okay. So think I could just simply do um, eligible person dot age, eligible person dot sorry, name dot age, eligible person dot occupation. Right. Let me see here. Yeah, what are they complaining about? Cannot match takes in a person. Oh, wait. Let me see if I can do this. Is it created already? Because we're using earlier in our person, we're using record syntax. I should have accessors for each one of these. They should create functions for us. I may be calling them correctly. Let me just do this. Age eligible person. Oh, right. Because we need to check to see if eligible person case eligible person of um if can I use I'm pretty sure I can use empty list of alternatives. Okay, good. Left error and call just here left um e um and what's this saying? Could not match e uh this is going to be we're doing the pattern matching of this guy. E underscore, we're not looking at that. Right underscore person name age occupation right um, don't care about the actual e that was created but let's do that again. Person name age occupation, see what happens here. What is it complaining? Left should have one argument was given two. Okay. Couldn't match type person with either. In the case alternative, in the pattern, right person. Oh, this just should be this. And if you end up getting something bound to P, this should be person P dot age, P dot occupation, P dot name, P dot age, P dot occupation. Still complaining about this. Hold on. There must be something here that I'm missing. Um, couldn't match the expected type person. Make this simple for me. And you write person dot name, person dot age, person dot occupation. This should be correct, but it's still complaining about something. Not match. Can I just do this? There we go. That makes sense. I'm an idiot. Okay, so here's what's happening. So I forgot that has with the maybe type, either also will return. It will either preempt if it gets an invalid error in the eligibility, it will preempt actually calling this constructor and will actually return whatever's value is here. Otherwise, it's going to go ahead and deconstruct this guy. Remember, it's going to unwrap the actual structure from the either type and give us the actual person that's in here. Because either is, we're kind of expecting that the left-hand side. Remember, either is actually specialized on the first, the left side for functor for fmap. So that's first left side is always totally ignored. Whereas with the right side, it's going to actually go in and correctly uh, move on with the next process. So if we go and do this, and we call load, if I do, let's say, eligible for retirement, and I call, let's say, some person named John Doe, he's 35 and he's a software engineer. They're going to end up getting variable not in scope. Eligible for just got it. Oh, okay. Eligible for the person to 3. Okay. Let's see here. This is a valid function. I'm not really sure what is causing T eligible for retirement. Okay. Let's say P equals person John Doe 35 engineer. Let's go and call. Oh, no, that should be right. It is calling just make sure that I understand this. It is doing name, valid name. So here in this case, we are trying to do an eligible age. and then we're getting a person, otherwise get nothing. So if I do eligible for retirement P, ah, that's the problem. Driving, EQ, and show. Oops. 1 second. That. Okay. And let's go ahead and call this here, this, this. These are all warnings that I'm just fixing up here. Um, and this. Um, okay. And right, right, a reprint of this. Okay, and let's call this here. Oh, I did reload it, deleted it. Um, do that, and do this, and we'll see that we get our what we expect, which is the left side is uh, going to give us an error called left, and it says that this person is too young. Now we can actually, write all the rules here, just like we did with the maybe monad, and get different validations until we get the right person. But the point is again, as with the maybe monad, either does the same thing. It'll error out things. In fact, you can add different validations, and either can actually, if I'm not mistaken, it will actually take each error and it will concatenate them. Um, and but for us to actually, for me to illustrate that particular issue, I'm going to have to step into a different realm. I'm going to have to actually go in and write a couple of validators, and I think leaving that as an exercise to you guys would be more appropriate, so we can actually go and try something else. So just a final show of this. If we do 66 here, just to show that this is all working as we expect, do eligible retirement P. You could see that it actually returns nothing. Interesting. It should actually return. Um, Eligible for retirement P. There we go. I don't know why it did not register that, but okay. And as you can see here, that we're actually getting the appropriate construction. So again, as with everything that we showed thus far, the point of these exercises of checking out list maybe and either is to get an intuition about how structures added between each individual transformation. And more importantly, although you can leverage, say, the bind operator like we did here to go and deconstruct and call fmap as we did, and then eventually get a flattened structure, um, do gives you this very nice sequencing facade that allows you to list your transformations and then um, uh, just write what the return value is once your validations are all checked. All right. Um, The last topic that I was going to cover, and I'm just going to briefly just touch base on this, is because really um, although it is a new operator, it's built on everything we've just discussed so far. Is the Kleisli composition operator. So the name might be daunting. The actual idea is very, very simple. If we recall what we've done so far, a lot of our stuff that we talked about in terms of monads and monadic transformations, we're dealing with function application to values that are being passed into a particular monad and deconstructed into the appropriate uh, m- uh, values necessary for a monadic transformation to execute. All right. But obviously, given two different functions that return monads, we want to be able to compose something. So say take given an A that returns a monad of A and given a B that returns a monad of B, we want to be able to, sorry, given an A that returns a monad of B and given a B that returns a monad of C, we want to be able to go from A to the monad of C without actually having to worry about a lot of these things, much like we would do with FMAP. If you recall, FMAP has the ability to actually go and say take, again, going back to our infamous list example, say this. Add 1 and times 2 and call 1, 2, 3. Um, this ends up being 357. All right. And you know that from composition, this is the same as if we do plus 1 um, dot fmap times 2, where we double it and we pass it to 1, 2, 3, and we get the same thing. All right. But we can also define, say, a function called like monadic compose. All right. Now, this is essentially the motivation behind the Kleisli operator that takes something that requires there to be a monad instance, and what it will do is it will actually take. Hold on. Let me write it here. um, Monad composition will take, say, something that takes in a monad M, and what it'll do is it will create a function that where the first argument is a monad, a function that takes a B and returns a monad a C, and it will then require you to pass in a function that is an A and creates a monad of B, and it will then return you a function that essentially, although you don't need to put parentheses around it, an A that returns a monad as C. Okay, this is very much a standard function composition. You can totally look that up, and you can see that monadic composition given two functions A and a value A is just f of g of A. Right. Um, complaining about and not. Oh, B of monad that constructs an infinite type. Now, when you look at this, you might be like, okay, this should have kind of worked because we're just simply taking a thing. But the error actually tells you what uh what is actually the issue. Um, what the function that we're passing in has a first argument. It's returning or it's expecting um uh a b to be returned, right? Unfortunately, G, our function, is returning a monad of B. All right, so we need to be able to somehow unwrap and then pass in uh, the B to F, right? So clearly, what this is asking for is context where, given a structure, we want to be able to first um, apply a function to the value that's wrapped in the structure. which we know is the very definition of fmap because we've talked about functions and functors, all right? And then from there, we want to be able to take that result and then deconstruct and create a new, get that value and move it along to the rest of the pipeline. That's exactly the problem here. The first case, if we create the G and returns a monad of B with fmap, that's going to actually give us two layers of structures of the monad, all right? Um, we don't want that actually necessarily to happen, right? What we want to happen is we want to actually call um, uh, join on this. And what this does is and again, this is because we don't have and what this is going to do is we're going to call it this way. Okay. We can't necessarily do this because this is going to throw an error saying that these are all infinite types, and that straight up application is not going to work. So you want to actually call the dollar operator like this, and this is actually going to end up creating. Or you can actually, I think, maybe call this, and this is going to work the same way too. Still complaining about it's not complaining about the right hand side, it's complaining about the left hand side. So we're going to use the generic dollar operator. All right. As soon as you see this dollar operator again, this is fmap. This is the applicative fmap. But the right hand side is not lifting, so we just need fmap. So and another way to write this is, of course, fmap f on g of a, and this should actually also be the same. All right. As soon as you see this, or see the infix operator like we used earlier, all right, you should be thinking bind, all right, because join plus fmap is essentially bind. So this can actually be converted, okay, into the following conversion here. We take g of a, and the return value is just going to be bound to as an input into f, all right, and this will do the same thing. Okay. You don't need to write any additional monadic composition because um, uh, like this, because this is essentially the Kleisli composition. Okay, this is the motivation behind Kleisli composition. If we look at the Kleisli operator, okay, and which we can do by just simply doing a fish, all right, um, you'll see. I think I might be missing an import somewhere. Oh yeah, I'm missing an import. In here, instead of doing this join, I'm going to just do this. Okay, and what's the warning here? Use to control the monad because except to import instances. Let's see if that works. T. So the Kleisli composition operator has built into the control.monad namespace. Essentially defines this exact pattern that we saw earlier. Okay, it creates essentially a function that'll take that requires a monad that has an instance defined for it, and will create a two argument function. The first one is a function that takes an A and creates a monad of B. Second one is a B that creates a monad of C, and it'll create an A that returns a monad of B, a monad of C, just like normal composition. If we look at the composition operator, this is exactly with the arguments flipped, as we can see here. Okay. Again, the left to right notation of bind is a result of the use of um, uh, result of how monads came about. Um, and they were a generalization of stuff that was done in IO and that was done left to right. So every monadic function operator is going to do left to right composition. All right. Just keep that in mind so it doesn't screw you up when you're looking at this. If we want this to look exactly the same and look at the type, we could just simply do type of flipped and you'll see it all matches up. All right. Um, The quickest example of this, I think, is just simply creating a simple greeting program. Let's, I think all of us seen, uh, say, uh, so we could just create a it's a this is actually it's probably easier just to go through this one example here. This one is straight up from the example in 18.7 where we have essentially a function that takes in a string and returns an IO string. We know that this is just going to be as nothing more than an alias, um, and let's say that we have some greeting that we pass in. We grab reading, and then we return essentially a get line here. All right. Then let's say that we want to grab the age out of this guy, and this is just taking a string and returns IO int. Then this is all doing is just nothing more than being an alias of calling hi and passing in this to um, let's say the composition of read um, return with the read. All right. So um, this here is something that we could probably just call read value, read age. It takes in something that's a reader. It could be any reader, but it takes in a string and returns an IOA. And read age is just simply doing what we just saw. Okay. It's just an alias. And all right. Now, if we call for a program that then returns an IO int, we could just simply call ask for age. And what this does is this will call this function and binding um ask if we call this guy here, this is can quickly show let's say 23, and you'll see that it'll return 23. Again, remember the deconstruction of return is behind the scenes in the REPL. IO will unwrap the underlying value and return it to the console because of how the show works for IO. All right. The point of all this is you could see that the Kleisli operator is doing exactly what we're expecting it to, and we can mix the Kleisli operator with the uh, um, some function compose that we've created, and then as long as all the types line up, everything will get lifted appropriately and passed on. All right. So in this case, read will take in a string, create an IO of A. And the IO is coming from actually return because read will actually just take in a string and then return whatever it needs. In this case, read is just going to create an integer if we just look at what read does. Okay. If we're expecting it to be an integer, it'll create an integer. So in our case, since we're asking for an integer, we're expecting it to be an integer. One second. We do not need this. If we're trying to generalize this, you could simply call this also read M, which will unwrap any monad that has a reader associated with it, and it will actually go through and generate that. So that's it for monads. There really isn't much else here. I encourage you to go through the chapter exercises. I'm actually going through that right now to see how we can, if there's particular demos that I want to see as a separate stream. Next week, we will be actually hope we're done with our journey for through semigroups, monoids, functors, applicatives, and monads. Next week, we're going to be having more applications of using this stuff with a case study, and that is covered in chapter 19 of the book. And this is a practical example that was built in the book. That's a case study that I think we should check out together. And there's some other examples too as well related to this. If I come up with, I'll let you guys know ahead of time. But I'm going to pause here to see if there are any questions because I see at least one viewer that's available on our YouTube channel. Okay. Um, if there aren't any more questions or any questions left, for those of you who are just staying on for the last 5 minutes, um, thanks for joining. I will see you guys all next week.